Alright, hello class. Okay, so we're going to look at a problem in two-dimensional kinematics. And this is a problem from the book. It's a good problem, so we'll use it. So let me read the problem first. It says a plane moving horizontally at 115 meters per second drops a care package from an altitude of 1,050 meters. So to start out with, the plane is moving, we'll call that velocity v naught. So that was 115 meters per second. And let's say it's moving a height 1,050 meters above the ground. And it drops a care package. I had to laugh when I first read this problem. I learned from a much older book. And if you look at any old physics book, they're always dropping bombs and shooting guns and stuff. And now we're dropping care packages. So. But, yeah. So, we want to know, the question is asking, where will a package land? And ignore air resistance, which, in reality, air resistance would have a huge effect on the motion of this object as it's falling. But, yeah, it's moving very fast. Starts out moving 115 meters per second, and then it's going to fall and, move even faster. So, that's what the question is asking, where is it going to land? But I want to add to that, let's figure out the velocity when it hits the ground as well. And I should have done this, or just, let's just write down our basic equations. Okay. So, just to save room on the board, I'm going to make the ground much closer than it actually would be. Or this is a really big plane. But, yeah. So anyways, this package is initially moving 115 meters per second horizontally. And we know it's going to fall to the ground, so it's going to take a path like this. And hit the ground. I'm going to label that point A. And what I'm going to do is I'm going to label the point directly underneath where the package was dropped. That's going to be O for origin. So we're placing our origin here, and we're using our standard, right and up are positive directions. And what I want to do is I want to make a table. If you look at these equations, we have initial position, initial velocity, and acceleration. So I want to make a table just kind of collecting this information. So we have R naught, V naught, and A. And each has an X and a Y direction. And what I'm going to do here is I'm going to draw a really thick line between them, which obviously you don't have to do. But I really want to emphasize, well, yeah, we'll get to that. We want to keep our X's and Y's separate. So I'm going to draw a really thick line there just as a reminder. Okay, so let's start out with the initial position of this package. So the X coordinate is 0, just because we set the origin there. The Y coordinate is H. So we have 0 and H. Now for the velocity, I should call this V0x. But, the plane was flying horizontally, so there's no, the velocity vector is purely horizontal. There's no Y component. So you can call this V0x or just V0. And the Y component of velocity is 0. Now, acceleration, why is this object accelerating at all? Well, because of gravity. And so the acceleration is going to be 0 and minus g. So there's no acceleration in the x direction. The only acceleration, because we're ignoring air resistance, is gravity, which is straight down. That's not causing it to accelerate at all in the x direction. So this is, again, it's not necessary to write down this table. But for some reason the camera and like what the video actually shows don't always line up. But I just want to make sure you can see the whole thing. Okay, so anyways, it doesn't hurt to make the table. Particularly if you practice a lot, you can just kind of go directly from this information. But what we want to do next is just write down the basic equations of motion for this particle. We're going to start with position, and I think I'll just write them here. And so the idea is, let's look at x, just for position. X equals. Now we're describing the x-coordinate of the position, and so what we can plug in, when we're describing, say, x or vx, the only numbers we can plug in are these three numbers. That's it. So that's one thing that's why I made this table in the first place. Really get this idea in your mind that when you're describing things happening in the x direction, you cannot use those numbers from the y column. And similarly, when you're describing what's going on in the y direction, you cannot plug these numbers in. So right now, if we're describing the x-coordinate, just, here, I'm actually going to erase these. I'll rewrite them later, but just pretend these don't exist. So these are the only things we can plug in. And notice we have three numbers to plug in, and there's three terms. So, oh, that's nice. Like when it comes to position, x naught, that's 0. Velocity, we plug in v naught, and so we have v naught t. So yeah, like the first term is going to correspond to this row, the second term corresponds to this row, and the third one corresponds to this row, which is 0, so that's it. X is equal to v naught t. And now for y, I'm going to put these numbers back. So again, here, I'll erase these for now. So that's what we can plug in for y. So now we have y naught, which is h. Now the next term is 0. So the next term we have v naught t, well that's 0. And then the acceleration term, because the acceleration is downwards, we have minus 1/2 g t squared. So, and now I'll rewrite these. So again, I don't recommend when you're working on problems to actually erase them and then rewrite them. But, I mean, it wouldn't even hurt to literally just cover them with something so you can't even see them. So when you're writing x equals, and similarly with vx. So if we write vx, we have, again, there's no position has nothing to do with it, so we're just looking at these two numbers. So we have v naught, and that's it. The acceleration term is 0. And if we write vy, we have 0 for the first term, and then at, so vy is minus gt. And so what we have here are the basic equations. We've completely described the path of this particle. We have, like at any time, between, this is at t equals 0, when the object is dropped, and it's going to hit the ground at a time we'll call ta. We're just labeling that point A, so that occurs at a particular time. I'm worried about running out of space on the board, so alright, so that'll occur at a time ta. And so between these two times, we know this path completely. You can plug in anything for t and get the x and y coordinates, because we know the initial velocity, we know h, and we know g. So anytime, as long as it's between these two values, we know the x and y coordinates. We can just calculate those. And similarly, let's say that we wanted to know, like, let's say I give you an x value. Like, say x equals 100 meters. can you find the y-coordinate? And the answer is yes, because we know the x-coordinate. And so if we know x, then we can solve for t, and then we can plug that time in here and get the y-coordinate. And there's a way you can even do this. Why don't we do this before we get to solving the problem even? Let's solve the first equation. T is equal to x over v naught. So what we have here, if you learned this in math class before, this is we're describing a path parametrically. Like time is our parameter. And so we're describing like each component, each coordinate in terms of this parameter t, but we can eliminate t and get like a relation purely between x and y. So to start with, we say t is x over v naught, and then y is h minus 1/2 g times t squared. So if we do that, then we have x squared over v naught squared. And I want to clean this up a little bit. And the reason I wrote it that way is this part in parentheses is just a number. It's a constant. It has units as well, but it is a constant. And so what we have here is actually a parabola. You think of the most basic parabola is y equals x squared, which would look something like this. Choose a different color. If we have minus x squared, it would look like that. Because here, this term with the x squared, we have a minus sign in front. And this is just a constant. Remember what that constant does? That affects all the y values, so that would just stretch it. Like if this was a big value, it would be stretched vertically. If it was small, it would be more compact. But it's basically going to have this shape. And then adding h just lifts the entire thing up. So like our final parabola would look like this. And that's basically what we have here. Just this part from here to here. So this is a parabolic path. And we can get this direct relation here, where like if I give you the x value, you can find the y value. Or if I give you the y value, you can find the x value. So we know this path completely. Like once we get to this point, we know everything about the path. And similarly, we can plug in anything for time and get the velocity at any point on this path as well. So we know everything we need to know to solve like any problem about the motion of this, I'll just leave that some general point. Yeah, like the motion of this object, we know literally everything that we need to know. Okay, now the question is asking, where is this object going to land? And it lands here at this point A. Let's give that some, let's say the coordinates are r comma 0. The x-coordinate I'm calling r for like the range of this projectile. And the y-coordinate, it's going to hit the ground, so the y-coordinate is 0. So what we can do is let's plug in the coordinates at point A. There's actually 3 of them. We have x, y, and t. So remember, these are general equations that apply to every single point on this path. But I want to plug in specific coordinate for just one point. So the x-coordinate, we have r equals v naught times ta. And in the y direction, y is equal to 0. And then we have h minus 1/2 g ta squared. So this is what we get just from looking at that one particular point. And remember, our goal is to find out where the projectile lands. We're looking for r. And so we know v naught, we don't know t. So if we can find t, then we can plug that in and find the range. If you look at this next equation, we know everything here except for t. So we can solve this equation for t and then plug it in here to get the range. Okay, another way to do it would have been Actually, I can still see it even though I erased it. I don't think you can see it on the camera, but yeah, because the whiteboard's not completely clean. Like if you want to go through and write it this way, again, another way to do it would just be to set y equals 0 and x equals r. So if you want to write it in this non-parametric form, yeah, just set x equals r, y equals 0, and solve for r. But either way you like doing it. Kind of equivalent, really. Because the way we're going to solve this is solve for t, and then plug it in the other one. Kind of similar to what we did before. But here we can write 1/2 g ta squared is equal to h. Or ta squared is 2h over g. So let's figure out what that is. We have 2h, so that would be 2,100 meters. And divided by 9.8 meters per second squared. The meters cancel out, the units are seconds squared, and then to find time, we're going to take the square root. So we will get seconds. Okay, so let's see what we have here. 2,100 divided by 9.8. To 14.29. So taking the square root of that, I'm getting 14.6 seconds. For time. So we know when the object is going to land, and then finding the range at this point is trivial. So we have v naught, which is 115 meters per second, times time, which is 14.6 seconds. So let's do that. And I'm getting 1,680 meters. That's over a kilometer. So, yeah, this thing's, I mean, obviously it would not do this in reality. You would definitely need to take air resistance into account if this was a real problem. Okay, so that's really all the question was asking. But I also want to look at velocity. And again, that's going to be kind of trivial because we know the time that it's going to hit the ground. So, well, this is going to be easy. Vx is equal to, so again, this is at point A. Vx is just equal to v naught, which is 115 meters per second. And Vy is going to be minus g, so minus 9.8 meters per second squared, times 14.6 seconds. Alright, so it's going to be around 140 or so. 14.6 times 9.8, yeah, 143 meters per second. And, well, minus. Yeah, so basically that's what we would expect. You know, up is our positive direction. So when it hits the ground, it's moving downwards at this speed and horizontally at this speed. And the last thing I want to do is convert this to polar form. So let's draw a triangle. We have Vx is 115 meters per second. And Vy is 143 downwards. And again, this is a right triangle because x and y are perpendicular to each other. So we can just use the Pythagoras theorem here. So 115 squared is 13,225. And 143 squared is 20,499. So let's add those. 33,724. So the velocity is 184 meters per second. Or that's its speed. That's how fast it's actually going when it hits the ground. So it has the components 115 and 143. And let's define this to be our angle and take the inverse tangent. So I'm going to take the inverse tangent of 143 divided by 115. So the angle I'm getting here is 51.2 degrees. Now this raises a question, like say you're taking a test and you want to know like the direction that you have to indicate what direction this object is moving. Do you have to write your angles in standard form? And no, you do not need to. So again, I should be able to look at your answer and see what direction this object is moving. And if you turned in this, I'd be perfectly happy with that. Because I can see what this angle is. It's 51.2 degrees below the horizontal. So like that's our horizontal direction. It's coming in at an angle. And again, if you have a picture, it's perfectly clear which angle you're talking about. Because you could also do like an angle with respect to the vertical. You could define that angle if you wanted to, which would be 38.8. So, they add up to 90. So you could have an angle with respect to the vertical or the horizontal. There's different ways of describing it. But as long as I can look at your work and see, what direction this thing is moving when it hits the ground, then I'm happy. And so a picture is always good. If you don't have a picture, standard form is usually the way to go. You could say, if you wanted to write this, you could say the velocity at point A is 184 meters per second at an angle of minus 51.2 degrees. So that'd be one way to write it, like in standard form. Because remember, we start at the x-axis and go counterclockwise. But if it's a negative angle, we'd go backwards. So you could write it that way. Or you could do 360 minus 51.2. So like 308.8, or just say like 309 degrees. That would be fine. That would be, going that direction, 309 degrees roughly. But again, as long as you indicate somehow that you know what direction the vector is pointing, I'm not saying there's one right way to do that. Okay, so we've got one more very important problem we're going to do, but that'll be on a separate video. So I'll stop this one here.